Alright, time for another DraftScience video presentation. So this will be a series of videos. Some new commenter showed up, Cyrus Thornton, or something like that, yeah. Claims to have some sort of credentials that he doesn't want to reveal for whatever, business reasons, no doubt. Whatever. But anyway, so he's made these elaborate arguments on essentially Newton's laws. And so I thought it'd be worth going through some of what's real and unreal. So before I begin, I guess we're going to talk about the action opposite reaction theorem. Okay. And I've just sort of pointed out that it's sort of misstated in the sense that it implies that there is something called inertia and that something reacts to being acted on. And my simple argument is that no, everything has its own circumstance. And everything has, you could call it inertia, but it's just your own circumstance, okay? And so you could be going this way, and this thing could be moving not at all, and something over here could be moving down. And that's its condition. And its condition is made out of a real circumstance. Now, we can't know the real circumstance because we can't see this quiet box. We can't see the control that says this is what not moving looks like in the universe. See, there's no pin, no beacon, no lighthouse, okay, that's saying, I'm not moving. This is what not moving looks like. So we don't have not moving to compare anything to, so we don't know whether this is part of a whole bunch of stuff, like the whole Earth. And all the stuff on the Earth all has this same bias. And then they can have relative changes happen to them as individuals. This one can change it, go this way instead, and this one can go this way instead. And now they have a change, but they're still doing this. Okay, so they still have the same bias. They just have individual differences within that bias. All right, so it's a little bit complicated when you start talking about the idea that this motion stuff is in any way relative. So the real point is all of the movement can be here, or all the movement can be here, or they can be divided 60-40 or 40-60 or 30-20. It can be divided up between something. It really doesn't matter for the purpose of understanding the fact that the two things are going to exchange their condition. And that's what's really happening, is you're just exchanging a condition. And there's a real condition. Somebody has the real stuff, and it's going to give the real stuff. And that's sort of the point. It's real. Movement is a real thing. There's a real component. All right? And it doesn't matter whether, like I said, this one has 60% and this one has 40% of the real component, or the other way around. It's still a real component of motion in a direction. Things are still moving into 3 dimensions by a real amount. And so for the sake of argument, or the sake of just having a rational conversation, we just decide to say this thing's got 100% of the motion and this doesn't have any. Just for the sake of the argument, to make the argument more coherent. All right, so what happens when something reacts? When something interacts, period. I'm just making a simple improvement, sort of like punctuated equilibrium as an evolution argument. Now, it's not Darwin, but I'm sure Darwin would have thought about it if you gave him enough time. So it's just a simple argument that there isn't really an opposite reaction. When you interact with something, okay, I'm moving this way, I'm going to interact with this object. The fact is, especially in the kinetic balls, it gives you the great example, what happens is this arrow just essentially goes from being in here to being in here. And that's what happens. This one goes from here to here. The two objects connect, they hit each other, and through that process of interacting, essentially motion here pushes into here, and a push is accepted. And by accepting the push, this object accepts the motion, and now it moves because this gave it away. So there's a deficit here. It did have this. Now it doesn't have that anymore. It doesn't need an opposite reaction to stop it from moving. What's stopping it from moving is the fact it gave away the thing making it move. So the simple thing to think about it is like it's a little squirrel, running inside of it. So something's moving. It's because it's got a little squirrel turning the wheel, the moving wheel. and the squirrel essentially just jumps and now spins this wheel instead. Or the whole wheel, goes into the other object. But you're just saying, yes, what happened? I changed. By giving something my momentum, I gave it away. And by giving it away, I changed my equilibrium. So I don't need something to decelerate me. All I need to do is give away my momentum. I give it away. I don't have it anymore. I can't keep going. All right? I don't have the gas. It's like you just gave the engine, it's just like if cars could do that, if they could just hit something and the engine and the wheels just went out from underneath the car and jumped underneath the other car, you'd get the idea that it doesn't need an opposite reaction to stop the other car. It stops because it doesn't have wheels anymore. It doesn't have anything moving it. So that's the slight modification. Now the truth is that there are two kinds of actions that can happen. You bang into something, it accepts the momentum, okay, and then it goes. So in that reaction, there's obviously no need of an opposite reaction to stop you because you got rid of your action. And the other one is the reflection. It doesn't accept it. You hit it, it doesn't accept the motion, and instead there's a reflection, okay, that ends up knocking you back. Okay, so that's a separate action. So you wouldn't really call that a reaction because you never acted. You never caused it to move, technically. I guess you could do this another way by saying you moved an object a very short distance into another object that refused to accept the motion, a rubber thing, and it bounces in and then pops back out again, and then that you're getting the reaction. So it is important to understand the difference between when you're moving something and you're just exchanging your momentum, transferring your momentum. There's no opposite reaction. Now, when there's a reflection, the thing bangs into something and comes back at you, that's clearly an action, a new action. And what's going to happen is you're just going to get a momentum arrow that you didn't have before. So you didn't have any arrow this way. And now this object's going to come back, hit you, and give you that arrow, give you the momentum. But there's no opposite reaction. You don't sit there and punch the guy in the face for giving you the momentum. There's no mechanism for an interaction that involves anything more than just transferring momentum or understanding that the momentum goes until it reflects. And when it reflects, then it's a new action. That's how I would explain it. Now, you think that's a violation of some sort of science decency law to qualify Newton's theory a little bit and just explain how, well, Newton didn't quite see it, energy as something being possessed by it. And I think it can fully be understood as something possesses the energy. If you throw a wrench in space, it's physically different than the wrench you don't throw into space. It has motion built into it. It has it inside its atoms. There's a real vector inside its atoms keeping it going. So it's a real thing that things have. Their direction in three-dimensional space is something things possess. Now, you don't want to believe that, that's okay, but you don't have any facts that say that can be impossible, that that's not a possible explanation. I don't think you could explain any circumstance where that can't possibly work as an explanation, because in fact it does work. All right. For every action, there's an equal and opposite reaction. So my point is that's not really true. Sometimes you just give the momentum away. You bang into it, it takes the momentum, you don't have the momentum anymore. So, like I said, in the classic example of the kinetic balls, the kinetic ball comes down, transfers the momentum, and that's all that needed to take place. There was no opposite reaction. It doesn't need to stop the other ball from moving. The other ball stops moving because it gave away its momentum. It doesn't have the go anymore. So it can't go anymore because it gave it away. All right. Is a summary of Newton's third. This summary is an introduction to the concept of Newton 3 for basic Newtonian mechanics teachings. The actual law is as follows. So, again, the fact that real physicists use this language. Don't pretend this is the best physicists have a whole different vocabulary they speak. So I think you're just talking a little bit of shit to sit there and imply and say that they all don't use these shortcuts. They all use the shortcuts. And the shortcuts don't tell you anything about the real physics, and that's the whole point of my critique, And the whole point of me qualifying this third law and saying the third law only really makes sense if you understand when you're giving it away, there isn't any opposite reaction. There just isn't. And it's only when your gift comes back at you could you say there's an opposite reaction. The fact that you gave the energy away is all you need to stop you from moving. When you pour your paint into somebody else's bucket, you don't have the paint anymore. All right. So, Philosophy Naturalis Principia Mathematica, 3rd edition, blah, blah, blah. So this is the translation into English of Newton's Latin. To an action, there is always an equal and contrary reaction. So, I mean, the words action and reaction imply the fact that two things have to interact, and the things have to interact because their force vectors have a conflict. You know, they're crossing each other. So they have to have a crossing vector, okay, and that crossing vector has to indicate some magnitude of a force. That is some amount of momentum. I would argue momentum is a force. It is carried by things. The force is what moves them. The fact that they have in their atoms a bias, more energy inside of the atoms is moving in one direction than it moves in the other direction. It moves more in one direction than it moves in the other direction. A fact of their atomic structure. Okay. To an action, there's always an equal and contrary reaction. Or, so I guess this was still Newton's quote, or the action of two bodies between themselves are always mutually equal and directed in opposite directions. So I don't know exactly what he meant by mutually equal. Yeah. Sorry. So the point is yes, the amount I give to somebody is going to be the same as the amount I lose. So in that sense, they're mutually equal. If I give away my momentum, it's a certain amount. The amount the thing gets is the same amount as the amount I give away. Now, of course, this is only true when you don't have friction and other things that are leaking the energy out. And then you can't transfer an equal amount of momentum. All right. To claim there is an equal and opposite reaction force, well, the point would be, I would argue to you, okay, that you want to play semantics games, you can go ahead and do that. I'm arguing that the force is inside of something. If it's moving because it's being pushed. There has to be a mechanism that's pushing the object. And on the nuclear level, the level of the atom, the force is the photon energy between the electrons and the protons. And that energy has a shape, and the shape of that energy is a vector in a direction. The atoms have the motion. And that's what you're doing when you're pushing on something, is you're organizing all the atoms in a direction. You're pointing all their helium nuclei in a direction. And by pointing their nuclei in a direction, it means they're going to tend to move in that direction. When the nuclei are turned in all kinds of directions, then you don't have any motion. But when all of them are turned in the same direction, then your motion is going to be substantial. Some high percentage towards the speed of light, for example. If I can turn all of the nuclei in your atoms to all be pointing in the same direction, you will go very fast in that direction. All right. Yeah, I'm not saying you have to believe this. I'm saying there is no evidence overtly that you can point to. Any experimental evidence this theory can't deal with or account for. There is nothing that proves it impossible. Okay. To claim there is an equal and opposite reaction force is a demonstration of a complete lack of understanding of Newton 1, 2, and 3. And I could just argue the same to you. So yes, we'll just get back into this verbal war about who knows Newton better. I would say that you people have perverted Newton. Okay, conventional physics has distorted and perverted Newton's statements into what he didn't say rather than what he did say. He made it clear on gravity, for example, that he postulates no cause because he didn't have one. And yet people will say what he knew, and that somehow he was saying the speed of the force is infinite, or something like that, when he never postulated. He didn't know whether it was the speed of light or not the speed of light. He didn't know. He didn't know enough to say one way or the other. And yet you've shoved these words into his mouth. Plenty of people have. All right. And again, even F equals ma. It's not Newton's formula. Newton's formula was F equals momentum over time. Change in momentum over change in time. Basically saying that essentially if there's no other force acting, that your entire acceleration is the change in your momentum, so it's your velocity. And so he's basically saying force equals mv. And then to imply his demonstration as an easier version or restating Newton is false. So I'm just saying that I'm saying you can say it's false. I'm saying it's wrong to say there's an equal and opposite reaction. There doesn't need to be any reaction. If I give away something, me losing the something is already stopped me from moving. If I give away my wheels, I can't wheel. Okay, and that's really all you're doing. You're just saying what was making me go, my momentum. If I give away my momentum, how do I still go? Oh, that's right. I don't still go because I gave away my momentum. All right, so there doesn't need to be any opposite reaction to stop me from moving. I mean, it's a pretty simple analogy, right? I mean, if you just thought of it as the wheels, and I have the wheels, and I give my wheels to somebody else, then I don't have anything to roll on. I can't move because I don't have wheels. If it's a jet engine, it's a fan. If it's a fan, I have a fan pushing me. I give away the fan, I can't be pushed anymore. I'm not being blown, I can't move. All right. Mass, moment of inertia. So mass, moment of inertia is another one of these phrases. Doesn't mean a whole lot. It's really just about a friction argument. I don't even. It's no point in really having to draw it. Moment of inertia just means that in circumstances where you have contact with something, and it can just be your two metal plates that are very shiny, and you end up sticking to each other, but you're not sticking molecularly. You're sticking, kind of electrically. And so you have a bond. And there's a certain amount of energy it's going to require for you to break that bond before you can start making this thing move. Well, friction does the same thing. Friction creates a force opposing your motion. But it's really not opposing your motion. It's really just a fact that it's made attachments. It has essentially molecularly bonded in some respects. And you have to break those bonds before you can get the thing to move. But it's not because the thing is preventing it. It's not because it's resisting it. It's because there's a mechanism that has to be changed before you can change this thing's motion. You have to overcome, those attachments to break it free. All right. Okay, mass, moment of inertia. So again, things in empty space don't have any moment of inertia. They're not attached to anything. They're not experiencing any friction. They're not putting up any resistance to change. They're merely saying, I'm not going to move until you force me to move. Give me a force, then I'll move. Give me some momentum, and I'll go. But they're waiting for you to give it to them. They can't move until you give them the moving force. Okay, or the change of occurs when an impressed force is applied to a mass. So again, there is no moment of inertia in empty space. If you're outside of all gravitational fields and all kinds of other bullshit, clearly there's nothing that needs to be broken. There's no force, that needs to be undone before you're free to go in a direction. So there's no force to counter. So if there's no force to counter, you freely move. And all you have to do is somebody just has to give you reason to do it, which is give you the paint. You're free to paint as long as somebody gives you paint. Your engine will run. Somebody has to just give you the gasoline. I mean, there's lots of analogies. You're not resisting running. You're just saying, I have to have gas to go. When an impressed force is applied, there is not just one, but two equal actions. So again, I'm arguing there aren't two equal actions. The one action of taking my motor and wheels and placing it in you is the only action that's necessary. You now have wheels and a motor. I no longer have them. I can't keep going. You can. The end. It's that simple. You're just giving something else what you had. You had a bias. You're little electrons and neutrons, and I mean your atomic nuclei, let's say, were all lined up. You took that alignment, hit it into something. That alignment moved right into the object you hit, okay? And the process of refilling you filled you with chaos. You didn't get refilled with alignment. You got refilled with things all being in different directions. So you gave away your order. You could argue your pattern. So you had a pattern that created motion. The pattern moved from inside of you into the other object at the speed of sound in the material. So if it was steel, at the speed of sound, you took that pattern and moved it from one object to the other object. Okay. When and impress force is applied, there is not just one but two equal actions. So I'm re-qualifying that to say that's only in the case of reflections are there two actions. And the one action is, again, a reflection, so you really wouldn't call it an action. It's a new action. But anyway, because the reflection could be delayed by hours or years or centuries. There's all kinds of time that can be before that reflection comes back, so you can hardly say that it's part of the action, because the reflection could take a really long time to make itself realized. Or simply stated, a primary action and a contrary action. So again, I'll just illustrate again. That's only true when there's a reflection. It's not true when you transfer your energy. So when two kinetic balls hit each other, one ball doesn't say to the other ball, stop. One ball just says go to the other one, and the go is in the form of here's my momentum. And there is no need for the second ball to say to the first ball, you can't move anymore. It can't move because it gave its legs away to you. It gave you the legs. It gave you the force. Okay, no new force. So obviously I'm not arguing that there's a new force. I'm saying that if you're going to imply an equal and opposite reaction or action, then you have to figure the action has a force involved. Clearly I'm arguing that force and momentum are the same thing. A force is momentum. It's just in a form, okay, different than the form of, linear motion. So the force can be in the form of an explosion that's going to take place if it's dynamite. And the explosion is going to go this way, and the explosion bits are going to go that way. Little pieces of momentum are going to fly off of the explosion in both directions. And so if anything's standing over here, it's going to get hit with a bunch of momentum going that way. And if something's standing over here, it's going to get hit with a bunch of momentum going that way. There doesn't need to be any opposite reaction. They're just going to accept the momentum. All right. The misunderstanding outside the classroom can arise because the action and contrary action, so we called them both actions, are measured in newtons. So again, this has nothing to do with anything, these units, this unit nonsense. So again, I'll say just plainly, a newton is a weight. And clearly a joule is a weight. A joule is a newton falling. So the weight of a stick of butter falling 1 meter, the landing weight is a joule. Joule. Anyway. And there won't be any rational counter-argument explaining how that's just not factually true. That we could measure joules in weight. Just as easy. We could just call a joule a certain amount of pounds. When a stick of butter hits the ground, it will hit with a certain force. That force can be understood to be a weight. A momentary weight. It's one piece of force. It's not a continuous force, so it can't maintain that weight. But for an instant, that will be the weight. So if you had a scale, the scale will jump all the way to like a pound. And the pound would basically be, that's what a newton in joules is. That's how many newtons are in a joule. Okay, so a newton is basically, a newton is 1/4 of a joule. Something like that. So it could easily, I've already stated that the momentum argument could be 2.3. So let's just stick with that. If you want to convert momentums, okay, Newton meters per second into joules, just multiply by 2.3 and you're done. And you know how many joules it is. So it could easily be assumed there is an inertial force and reaction force because the measurement in newtons. So again, it really doesn't matter. If you understand that a newton is a certain amount of weight and that a joule is that weight after it fell a meter, which means it's got to weigh more, and 2.3 times more, pretty much. Most people outside of physics do not understand SI or meters per second squared. Well, again, this is just all kind of baby talk because we're really arguing about physical concepts. I mean, whether or not there is an action and a reaction, or whether in giving something your momentum that somehow there's a stopping force, that somehow it's necessary for somebody to stop me from moving when I give away my moving engine. The only thing that's making me move is the engine. Without it, I can't move. Without, it's like, you know, it's more critical. So I should say like feet. Without my feet, I can't walk. Okay, so if I give away my feet, I can't walk. I don't need somebody to stop me from walking. I'm already not walking because I gave away my feet. All right. In the prelude to Newton 1, 2, and 3, he offered a list of basic definitions. The forces he defines are follows. So again, let's understand, this is 1672. I mean, this is a long, long time ago. And clearly, it would be idiotic for us to think that Newton had it all figured out, because Newton didn't know those electrons and protons and atoms and all of that stuff. He didn't know all the contextual information we have about all the little stuff that's moving inside of objects and how they could have something to do with how the object manifests. Just as he didn't know anything about all this magnetic stuff and the fact that you can change the orientation of the domains and make the substance magnetic by having them all pointing in the same direction. And the same thing could be true for the internal dynamics of things called motion. Motion could have exactly the same kind of dynamic as being comparable to domains. And the more atoms you have going in a direction, the more likely it is you're going to go in that direction. It's spread over all your atoms. All your atoms have to be dragged along. None of your atoms move because you say move. All the atoms have to be moved because their physical mass has to experience a force that compels them to move. They all have to be pushed. There's no magic just move because you say move. All right. The impressed force, the motive force, the centripetal force. I mean, all of this stuff is sort of, you know, again, I would argue that if Newton were alive today, he would recognize that the force is all the same force. It's motion, period. And it doesn't matter what the mass is, whether the mass is an electron, a proton, a whole atom, or numerous atoms. It doesn't matter. All you do is add up how much of this stuff called mass is moving, and that'll tell you what a force is. The force is in the form of photons or some other kind of nuclear bits moving into an object. So the force can be invisible, but it's still the same thing in that it's a bunch of mass moving in the same direction. Now, yes, light isn't a bunch of mass, but it's clearly mass. And it clearly does move things, but it takes a lot of it to actually physically move something. All right, there is no reactionary force, but again, the rhetoric implies it, and Newton's own statement implies it, so that's all I would argue. It's implying a secondary reaction. There is no second reaction, there's just you giving away something. And that automatically creates the stopping force. You've automatically stopped by giving away your go. Okay, that is make-believe. So it says you. And by the way, in the definition section, he defines quantity of motion, the modern term for momentum, as P equals mv. Now, we already know that, right? But isn't that the truth of it? He already understood the concept. And when he said quantity of motion, what the hell do you think he meant? Do you mean he thinks it's something other than energy? What did he think? If there was going to be a word today that he would pick to be put an equal sign next to quality of motion equals, what do you think he'd say? Of course he'd say energy. Oh, of course, yeah, we didn't have the word energy, but that's certainly what this quantity of motion stuff is. So again, this is all just such word games. Clearly Newton defined motion of the things in the universe based on momentum. There was no notion of any mv squared, of any kinetic energy concept. All of that is nonsense. He clearly understood potential energy, and he understood it as being circumstantial. That is based on what field you're in. But anyway, he then immediately follows that definition by defining the forces as separate quantities from momentum. Well, you say he's defining them as separate quantities, but no, he's not. He's just qualifying them. It's sort of like calling separate sciences. Biology is a separate science. No, he's saying physics underlies it, and you can get more specific if you like, but they're all in the category of. So, that's your retextualization. That's your restatement of Newton. Force does not equal momentum, says you. It clearly does in Newton's terms. F equals ma is originally written as F equals momentum over time. Change in momentum over change in time. If we make time 1, we already have that. We have the answer right there. F equals momentum. The force is momentum. It will be converted directly into momentum. The two things are convertible. You can always convert the momentum into the force and then convert the force into momentum. And it'll always be the same quantity, because the force isn't really something different. It's just you're saying the force, the momentum, can be in lots of forms. It can be a bunch of photons going in one direction. It can be atoms going in one direction. It can be parts of a body moving. Okay? It can be anything moving that has mass. That's the form of the force. And some of the moving things we can't see with our eye. It doesn't mean they don't exist. All right. Force does not equal momentum. I think in Newton's mind, I think they were synonymous. And I think he overtly said it. Like I said, he clearly states it in his formula. F equals ma. F equals mv is what it really stated. This is a violation of Newtonian mechanics, says you. Hence, read Principia for yourself. Well, I don't read Latin. And frankly, Newton wasn't much of a writer, in my opinion. Frankly, from my perspective, he didn't explain any of this in any kind of terms that are, easily understood. Okay, and he certainly does not define momentum or force as a scalar quantity. So this is just more absolute nonsense. Of course he did. Of course he understood that the energy, the momentum, is a vector. So you're saying he didn't think of it as a scalar. Of course he didn't think it as a scalar. Of course it's a vector. It's a direction. And if he was to see the kinetic energy formula, well, he did see it, and he despised it and said it was rubbish and nonsense, but he certainly didn't see it as the kinetic energy formula is something different. No, he didn't see that as a scalar. That's clearly a vector too. You're just making up this crap. Okay, this title you've given these things, are just absolute nonsense. Write it down. They have the same things in them, m and v. So you're saying because I squared it and put a half in front of it, all of a sudden I made it a scalar instead of a vector? What an absolute pile of shit. I mean, everybody knows that the energy you're talking about, if I have a train going down the track, what, are you going to lie to me and say you mean the energy going in all directions? No, there's no energy going in all directions. You're saying the mv squared is telling you how much energy is going this way and this way and this way and this way? No, it's one way it's going. So what is this, I don't even know what to call this crap. But this is just, it's crap. This is the crappiest of your arguments, is to play some semantics game and say that you somehow qualified one formula as a scalar and one formula as a vector quantity, when obviously there's no indication that they have anything to do with this nonsense. They look exactly the same. They're describing exactly the same quantity, the motion in a direction. How much stuff will this be able to move in the future? How many joules of energy does it possess? That's what both of them are telling you. This is pathetic. He defines them as a vector quantity, of course. Yeah, a right straight line. And that's exactly what the kinetic energy formula is stating also, is a straight line. You can't do the 1/2 mv squared math unless you establish straight lines too. There's no math to do if you say, well, 1/4 of the energy is going this way and 2/5 of it's going that way. Well, then it's not the same energy. Then you'd have a different formula for each one of those vectors, wouldn't you? Yes, you would. Okay, hence momentum does not equal energy. Oh, that's no hence. That doesn't follow at all. So just more nonsense. Energy or kinetic energy. Well, what is there? Energy, kinetic energy, momentum. Which one is real? You think all three of them are real answers. You can have energy, or you can have kinetic energy, or you can have momentum. Which one? I mean, you can't have all three. All three are saying completely different things, so this is just baby talk. Trying to equate a vector quantity of momentum with the scalar quantity. Again, just completely made up. There's no scalar quantity. There's no aspect of the equation that says this is a scalar quantity. It doesn't have any direction. No, every single time they use the equation, they automatically assign one going this way is positive, going that way is negative. And the same is true for, you have to do exactly the same thing with momentum, because the equation doesn't sit there and have an arrow over it. It doesn't point in a direction and tell you ahead of time. You have to establish, well, this way is going to be positive and that way is going to be negative. It's exactly the same. Like I say, how can they possibly argue the formulas are different when the only thing you changed is you put a half in it and you put a square on the velocity? How the fuck could they possibly be different equations and different categories of equation? Somehow that you use them in some fundamentally different way when they have absolutely no features in uncommon. They have exactly the same features, and yet he's saying, you know, the cat and the cat and the cat. Well, somehow that cat's a dog. No, they're both cats. Okay, you can call it a dog, but you're just fooling yourself because there's no evidence it's a dog. Okay, with a scalar quantity of kinetic energy is yet another violation of Newton mechanics. Well, again, there's no violation of Newton mechanics. You have to prove that one. Where did Newton ever make such a silly distinction? Show me any place. I mean, of course, this stupid kinetic energy formula didn't even exist, so of course he didn't know it was a scalar or whether it was a vector quantity or any of that horse shit. All he knew, it was invented by his worst enemy in life. It was absolute crap, and that's what he said it was. He didn't even pay any attention. It was such a stupid idea from Newton's perspective that he spent no energy arguing against it. None. He made a couple of sentences in letters to people saying what a crackpot idea. And that's the extent of what he gave a shit. That's how stupid the idea was. How irrelevant the idea was. So don't tell me what Newton would say. Oh, it's a scalar. Bullshit, he would say that. Newton would say, well, yeah, if you're going to invent this mv squared, I'm quite sure. And again, remember, it didn't even have the 1/2 in front of it then. So it was invented as just mv squared. So this guy is telling me if I write mv, E equals mv, or I write E equals mv squared, that somehow you can just look at those two equations and, oh yeah, that's a vector quantity, and oh yeah, that's a scalar. What a pile of crap. I mean, like I said, this is the lamest of these bullshit arguments. Okay. Yeah, too stupid. Sorry, that was too stupid. No offense, but that's just too stupid an argument. It's just too lame. Anyway, so then Piero chimes in. Oh, Piero just keeps typing one pile of shit after another pile of shit after another pile of shit. I mean, he just drones on. He has no evidence for any of this crap. He can't support a single thing he says with a piece of frickin' evidence. All right, there is an equal and opposite force. The force of what? So again, in the example of the kinetic ball, he thinks there's some opposite force that stops the ball from moving. Giving away its momentum, no, that didn't stop it. It has to be physically stopped by some force. No, it doesn't. For example, if I push on a wall and nothing happens, there's always something happening. So again, that's more bullshit, right? There's something happening. You're pushing on the electrons are pushing on other electrons, are pushing on other electrons. So the force is going into the object, and by nothing happens, you're saying everything doesn't move. So yeah, if nothing moves, okay, if nothing yields to the pressure I'm applying, then what happens? Oh yeah, then I'm going to get the reflection back. That's because the tension in the wall is pushing back exactly as hard. Yeah, only if the wall isn't moving, right? So that's not really a good example of action and reaction, because you didn't cause an action, did you? You didn't move anything. So it's not really a good example of action-reaction. A good example of action-reaction is, yeah, you push and the wall moves. Now where's the reaction? My hand moves, the wall moves, everything moves. There's no reaction. I'm losing my momentum. My hand moves slower as I make the other thing go faster. I mean, I lose energy. Okay, if it bends until the tension is equal to the pressure of my push. So again, more circumstances where now he's talking about something that's more complex, where you're going to push something till it bends. And let's understand, all of it is dependent on you being on the ground and being able to force anything with pressure. You can't even manifest pressure. So if you're in space, it obviously is a lot more difficult to push on something because you don't have any of the ground pushing to push with. So it's more about what the ground is doing than what you're doing when you're on Earth pushing. Or else it breaks after giving back all of the force it took to break it. So it won't give back all of it, and that's when you start having losses. It's because you start deforming objects with pressure, and lots of other things start happening when your pressure doesn't work. Okay, so when your pressure doesn't, when nothing yields to your pressure, then your pressure can start to do damage. All right. So, but anyway, I don't even think, in substance, any of us would disagree about the basic idea that, well, no, it is a disagreement. I mean, it's just change, right? You're changing the circumstance. You're taking something that is moving, you're moving the motion into something else. And the simple argument is you can understand that if all I'm doing is taking the quantity of motion as Newton understood it. Newton would understand the quantity of motion moves from one object to another object. That's the only action that needs to exist. By losing it, I've already changed. I'm changed, and the thing I gave it to is changed. It's changed because it now has it. I'm changed because I've lost it. And I'm just arguing, I think that's a more sensible way of describing the circumstance, rather than implying that there needs to be a stopping reaction force, that the environment has to react. So back up in a spaceship, the point would be is that if I fire something out of the ship, I don't need the space to react. I don't need some action from space. The mere fact that I gave something away that had momentum means I've changed my internal condition. I gave away this way, then the stuff I have is now got to have a bias this way. So if I was moving this way and I give it away, then I go to zero. But if I'm at zero, if I'm at equilibrium and I give it away, that is, I blow a couple of joules to shoot 2 kilograms in a direction, then I have to go this way because I gave away to this way. That now I have to have an imbalance. Because I was balanced. So I must have had this opposing this. If I give away this, then I still have this. And so now I'm going to go this way. That simple explanation, I think, is probably close. I'm just suggesting that's closer to the truth. And I'm suggesting you're not going to find any experimental evidence demonstrating that that can't be true. That would be my argument. All right. So this isn't a substantial disagreement. This is just nitpicking in the sense that they're saying nobody's allowed to do any revising of Newton's theories. All of Newton's theories have to stay in Newton's exact words, and we cannot in any way enhance them. I would argue that changing F equals change in momentum over change in time into F equals ma was not a good change. All right. So enough of a video. And then we'll do, he has, like I said, he has 3 parts here. So it's probably worth going through them and just accounting for the misrepresentations and making it clear that yeah, this isn't a big deal. But I still argue that it occurs to me, okay, that it's a little too simplistic. Newton is underdeveloped, and he should have gone. He could. After 300 years of time, past 350 years, we can do a little better in phrasing what the third law represents, which is the fact that you losing your energy means you are changed, and you don't need an opposite reaction. The action of giving it away is the only action you need. All right. And so, till the next time, and such and so forth and whatnot. This has been a DraftScience video presentation and such.